So welcome to week 3, Memory Management and Virtual Memory. So in this we are going to discuss about memory hierarchy and hardware, what is contiguous memory allocation, paging and segmentation, and then we will discuss about virtual memory and page replacement algorithms, and then we will talk about what is thrashing, TLB, that is the translation leukocyte buffer, and memory mapped file. So let's start. The memory hierarchy. As we know that all the memories are not equal, we have certain trade-offs between the speed, cost and size. We are having SRAM, DRAM, ROM, magnetic tapes, SSD, flash drives, storage space on internet. There are multiple types of memories. Right? So, and each have a different speed, cost and size. Like if we talk about in terms of RAM and our physical storage, that is the hard drive. So the size of hard drive is large enough in comparison to cache or RAM, but the cost and speed differs as well. The RAM and cache are speed faster than the hard disk. The goal of memory management basically is to make the vast and the slow disk storage to feel as fast as possible like RAM, because if your processor is going to directly deal with the storage which is slow, so the speed mismatch will be there and you cannot utilize the processor because processor is very fast in comparison to this disk storage. So we have a memory management unit which makes this operation pretty compatible. So if we see this example, we are having different types of memories like registers, caches, main memory, flash disk, traditional disk, remote secondary storage, and so on. This triangle shows the size of the memories. Like registers are smallest in size, then cache, then main memory is bigger, and the remote secondary storage is the largest memory. These registers, cache are on the CPU, main memory is also on your computer. These registers, cache and main memory are called as the primary storage, whereas flash disk, traditional, all other are called as secondary storage. If you see the access time, the more you go on the top, the access time is faster. These are the fast memories. But if you go towards the lower side, the cost is lower. At the upper side, the cost increases because the size is smaller, but the cost increases and the speed increases. Whereas when you go to the bottom, the access decreases and the cost also decreases. So why this memory management needed? There are multiple programs in the computer's memory which can run simultaneously. So when we are trying to run multiple programs concurrently, we need to run this program efficiently so that one process cannot modify or cannot access the memory space taken by other process. And we want to utilize the RAM, which is very limited in size, to its fullest potential. So, and to and to provide a level of abstraction also, that to provide the programs a simple uniform view of memory, hiding the complex physical details. We require memory management, that is the MMU, memory management unit, to fulfill the demand, protection, efficiency and abstraction. So the basic hardware which we use is the CPU and memory. This CPU can only access the instructions and data that are in the main memory or in the cache. So every data or instruction from the secondary storage we need to load in the main memory or in the cache, only then CPU can access these. So for this purpose we require base and limit registers. Base and limit registers are a way of protection. Each process in memory has a base address, which is also called as the start address, and a limit, which is the size, that from which address it begins, and what is the size in memory. So every memory address generated by the process, which is the logical address, is checked against its limit register. If it is within the bounds, it is added to the base register to form the physical register address. Look, CPU generates the address, then the base value. If it is greater than the base value, then we go on, and if it is less than the base plus limit, then it is a valid address. Otherwise, it is an illegal address. Address binding. Address binding is, look, whenever we execute a program, the mapping of programs, instructions, and data from disk, because my program data and instructions are stored on the disk storage, right? We need to load them into the memory, which is RAM. This all transfer can happen at different times. We can do it at compile time, we can do it load time, or we can do it at runtime. Compile time is when the memory location is known in advance, that when where your program is going to be loaded, we have generate the absolute code. Since the whole program is loaded at once in the main memory, we generally do not do it because it takes lots of memory. The other stage is load time. At the load time, we can perform the address binding. If memory location is not known at the compile time, the compiler generates the relocatable code. The final address binding is done at the load time. And the execution time, which is the runtime, which is also called as dynamic binding, the binding is delayed until the process is actually running. This requires your special hardware about which we just discussed, that is the MMU, and allows for processes to be moved in memory during execution. This is the one of the most common and flexible method which we use for address binding. So if you see here, the source program, whichever you are writing in C++, Java, or any of the source program, the compiler converts that code into the object file. This is the compile time process. Then, using the linker and other object files which are required, this code is converted into the executable file, which is called as load time. Then this executable file is loaded into the loader with dynamically linked libraries, which are also called DLL, and then the program is loaded into the memory, which is called as execution time or runtime. Now, what is the logical address space and physical address space? Logical addresses which are generated by CPU. It is the address that the program thinks it is using. So it is the address of in the RAM basically, so which the program thinks it is using. So it is the address space, logical address space, and the set of all the logical addresses is called as logical address space. On the other hand, the physical address is address which is seen by the memory unit, the actual location in the RAM. Logical address is the actual address in the storage, whereas your physical address is the address in the RAM. The set of all physical addresses is called as physical address space. Memory management unit is the hardware device which we use that performs this runtime mapping from logical to physical address space, like from secondary storage address to the main memory address. For example, a program works with an address 100. The MMU's relocation register, that is the base register, has a value of 14,000. So physical address will become 100 plus 14,000, that is 14,100. So CPU generates the logical address, MMU converts that logical address into the physical address and maps to the physical memory. Now dynamic loading and linking. When a routine is not loaded into memory until it is called, so we keep the initial memory footprint into the process small, handling the program by itself. So you load the program as much it is required. You are not loading the whole program at once, which the files which are required in memory, you are just loading those files in memory. And dynamic linking, on the other hand, whenever we execute a program, it requires lots of other files also for its execution. So dynamic linking is again linking of all the shared files. In Windows we have DLL files, in Linux we have SOAP files. So it is postponed until the execution. So whenever we require a file, only then it is linked to the program code. So this is also handled by the operating system itself. So if you see here in a static linking, this is the example of a static linking. All the codes, whether it is a library A code or library B code, these are all combined into a single unit, a static program copy, and those are loaded into the physical memory. Whereas in case of dynamic linking, we execute program modularly and we wait if a code is needed, if a module is needed, only then it is loaded into the main memory. So main memory copy, it points to shared memory A in system memory and it points to shared memory B in system memory. So we just take a reference over here, we do not copy the whole program. Now, memory allocation schemes. When we are allocating the memories to the processes in, so either we have the contiguous memory or we have non-contiguous memory. Contiguous memory is each process is contained in a single contiguous section of memory. For example, if this is our memory, in some part there will be operating system, then we create some of the partitions of memory and a whole process is loaded in a single partition. Like process P1 is here, process P2 is here, and so on. This is called as contiguous memory. That whole program takes a single contiguous memory block. It is works for, so the operating system resides in the low memory, and this one is the low memory, and after this it starts all the high memory. So user processes goes in the high memory. Now this method is simple, but it is not flexible. The reason is, first of all, memory is divided into the fixed size partitions. So a process must be fit into a partition. Now, for example, yes. Now, for example, your memory, we are dividing the memory into the fixed size partitions. We can divide the memory in fixed size partitions or we can divide the memory as variable size partitions. Fixed size partitions, that the sizes are fixed. Now, first of all, process must fit into a partition. If the size of a process is greater than the partition, it cannot fit here. So we cannot execute a process whose size is greater than the partition. Now, if so, that is a problem. Another problem is, let's say this is my process and these are the partitions, and just a minute. Yes, and the process size is smaller than the partition, because it is very rare that process size and partition size are exactly same. So either it will be greater than or it will be less than. If the process size is greater than the partition, we cannot load the process in memory, so we cannot execute it. If the process size is smaller than memory, the smaller than the partition, then if you see, this space is wasted here, the space within a partition, it is called as internal fragmentation, because this is the unused memory space within a partition which cannot be used. If we use the variable size partitioning scheme or dynamic storage allocation, that means the memory is not pre-divided. The operating system keeps a table of allocated and free memory holes. So when a process arrives, it is allocated to a hole that is large enough to hold it. So already we are having some of the partitions. We check the variable size partitions we are having, and we check that the process will fit in which partition. Now there are again certain strategies that which process will fit in which partition. One is the first fit. We allocate the process in the first hole that is big enough to accommodate that process. Best fit is we allocate the smallest hole that is big enough. So leaves the smaller fragment. Don't leave the large fragments. And the worst fit is allocate the largest hole to the smallest process, which means we will have a larger hole available which can be used for other process. Look, for example, if this is our memory, let's say these are the variable partitions, so these partitions are small, these are the large. The first fit, let's say this partition is of size 10, this partition is of size 20, this partition is of size 30, and this partition is of size 40, for example. So first fit allocates to the first hole that is big enough. Let's say my process size is 12, so it will be allocated to this partition. Best fit, let's say my process size is 18, so again it will be put it into the 20, because this partition can accommodate this process with leading a smallest internal fragmentation. But worst fit says put the smallest process in the largest hole. So what if I'm having a process of size 12, I will put it here so that rest of the 28 it can be used to accommodate another process. So it leaves a large fragment which might be used for other process. This leads the problem of external fragmentation, because once the processes are loaded and removed, there are number of smaller chunks in memory. These are very small enough so that these cannot be used to accommodate a process. These are scattered pieces of memory which cannot be used for any loading a new process. So this is called as the external fragmentation. So fragmentation, we can have internal fragmentation, external fragmentation. Internal fragmentation when memory is wasted inside an allocated block. Whereas external fragmentation when total free memory is sufficient but it is not contiguous. As we said, just saw in variable partitioning. The solution of external fragmentation is compaction. We shuffle the memory contents so that all the occupied processes goes at one side and all the free memory together goes at other side to make a large block. This process is very expensive, so since we need to move all the processes in memory from one place to other, so we need to perform a lot of binding also for this one. If you see in this diagram, internal fragment, this is a memory space, this is a fixed partition, this is a fixed partition, fixed size partition. This is the used space and this is the fragment because it cannot be used for other processes. This is the used space, this is the space which can fragment. So these are the internal fragmentation. On the other hand, if we take the variable size partitioning, this operating system is in the low memory, then process 0, process 6, process 2 and so on. If you see here, these are the smaller chunks of memories. These are very small enough, so all of these are sufficient enough to hold process 7. But since process 7, these memory chunks are not contiguous, so we cannot load process 7. So this is called as external fragmentation. Now, to solve the problem of external fragmentation, we use the concept of paging by allowing a process's physical memory to be non-contiguous. So how we do it basically? The logical address space is divided into the fixed size blocks called pages. Physical memory is divided into fixed size blocks called frames. So actually one page size is equal to one frame size. Logical address has the pages and physical memory has the frames. The operating system maintains a page table for each process to translate logical page number to the physical frame number. So if you see here, CPU generates a logical address. It has page number and a offset. Since size of page number is say same as size of frame, so offset is going to be same. So the offset is directly transmitted as it is. Now from the page table, for the corresponding page, we find out the corresponding frame number. This frame number is mapped here, so we get the physical address. And from this physical address is the address of physical memory. For example, a process logical memory, we are having 4 pages, and the physical memory, so we are having frames from 0 to 7. Page 0 is loaded in the frame 7, page 1 is frame 2, page 2 in frame 7, and page 3 in frame 4. So we need to perform the address translation. So logical address is page number plus offset, physical address is frame number and offset, as we saw in this example. Now, page size, let's say page size is 4 KB and my logical address is 7500. So page number is 7500 divided by 4996 because 4 KB, which comes out to be 1 integer given. And the offset comes out to be 3404. So page table says that page 1 is in frame 2. So physical address becomes 2 times 4096 plus 3404, which is this one, which comes out to be 11596. So this is way how we calculate the physical address. To implement the page table is basically stored in main memory. So we maintain a PTBR, which is called as page table base register, which points to the start of the page table of the current process. It means that every logical memory access requires 2 physical memory accesses, one for the page table entry and the other one for the actual data instruction. So this will actually cut your performance in half because every time you need to perform the 2 read operations to the physical memory. So the solution for this, we use a translation look-aside buffer TLB. It is a very fast small hardware which we use for the caching of the page table entries. So this is our page number and this is our offset. So extract the page number P and use it as the index into the page table. Extract the corresponding frame number F from the page table. Replace the page number P in the logical address with the frame number F. So let's say if this is our logical memory, this is the page table and this is the physical memory. So page 0 is loaded in frame 1. That means in frame 1 page 0 is there. Page 1 is loaded in frame 4 according to the page table. So page 1 is loaded in frame 4. This is the paging hardware using the TLB, that is the translation look-aside buffer. So since we do not need to go every time to the page table which is in the physical memory and which is in the RAM, so we go for the TLB. TLB is a small hardware which works as a cache actually. So CPU generates a logical address. First of all, we check whether this page number is in the TLB or not. If it is, that means if it is a TLB hit, we directly get the frame number and the physical address is generated. If the page number is not found in the TLB, which means it is a TLB miss, then we go to the page table, then we find out the corresponding frame number and update the page table address. So since another way of allocating memory is segmentation. One is paging, and that is the contiguous memory allocation. Another one is segmentation, which is the non-contiguous memory allocation. So, um, whenever the segmentation is basically is to support the user's view of memory. Like for example, when I am thinking of my code, I will think that function 1 is stored in one memory partition, function 2 is stored in one memory partition, my heap is stored at one place, and my stack is stored at another place. So each segment here, all of these are called as a segment. Each segment here is a logical unit basically, which has a name and a length, and addresses here are specified by segment number and offset. Unlike page table, in page table it is specified by page number and offset. Here it is segment number and offset. Instead of page table, we have here a segment table which maps segment number to their base address in the physical memory. And each entry again also has a limit, which is the length of the register length to for the protection, so that no two um, physical addresses can interfere each other. One memory location should not be able to update others memory location. So if you see here, the code is in segment 0, the data is segment 1, the heap is in segment 2, the stack is in segment 3, and so on. And as per the segment table, each so limit. So code segment 0 is in code 30. Data is in 1300, that is 25, the base address, and so on with as per the base address. So if we compare paging versus segmentation supports the user's view, programmer's view, whereas paging doesn't support it. Paging is completely done by operating system. In paging, your address space is one dimensional, whereas in the segmentation, the address space is two dimensional. Paging has the problem of internal fragmentation, whereas external segmentation is for external fragmentation. In paging, we use the table as page number and frame number, whereas in segmentation, the segment number is base address and limit. In paging, it is easy to share pages, whereas in segmentation, it is easy to share the entire segment, not just the pages. Now, let us come towards the virtual memory. Now, the core idea of virtual memory is separation of a logical memory from the physical memory. Let's say that the logical address space of a process can be much larger than the physical memory. Let's say my process is larger than the physical memory. So only the parts which are currently executed will be in the physical memory. The rest of the parts are reside on the disk, which we call as a swap space. So what happens? The part which is required for the execution, only that part is loaded into the main memory. The rest of the part is being held in the on the secondary storage, which is called as the swap space. So it gives a illusion to the memory that the process size is less than the main memory, but actually the process size is larger than the main memory. So the benefit of this scheme is there is no constraint on the size of physical memory. You can execute the processes of any size irrespective of the size of the RAM. So to implement the virtual memory, the concept of demand paging is used. It is a paging system where pages are only loaded into the memory when they are needed by the executing process. So we use the term for this lazy swapper. A lazy swapper manipulates the entire processes, that which process needs to be in and which process needs to be out from the memory. So for this purpose, we uses a valid invalid bit in the page table entry. So valid bit is if the page is legal and is in memory, then it is said to be valid bit. Invalid if the page is either not in the logical address space or it is valid but is currently on disk. So like for example this, we put a valid invalid. Page 5 is in 9, page 4, like page 6 and page 7. Since these are not in the memory, so we put a invalid bit. All other pages are in memory, so we put it as valid bit. Now, the page fault. The process tries to access a page that is marked as invalid in its page table. So what will happen? There will be a page fault. This is called as a page fault. You're trying to get a page which is not in memory, which is not in the page table. So a trap will be sent to the operating system. It will check if the memory reference was valid. If it was invalid, it will terminate the process. If valid, it will proceed. So it will find a free frame in the physical memory. Then it will schedule a disk operation to read the needed page from the free frame into the free frame. And when the disk read is complete, update the process's page table and mark it valid from invalid. And then restart the instruction which is caused by the page fault. So look, what happens? Load M, reference is generated. We find a invalid bit, which is this I. So it will send a trap to the operating system. The operating system will read that page from the backing store, that is the secondary device, and bring that page into the physical memory. And then it will reset the page table. So when it will reset the page table, instead of this I, it will become V because the page is now in physical memory. So from the invalid bit, it will be set to the valid bit. And we restart the instruction. So when we are going to restart the instruction, the next time again we will reference the page in the page table and it is valid bit. That means the page is found in the memory. So if there are no free frames, then what to do? Then in that case, we need to replace one of the existing page. So for this one, what we need to do, we need to find out the victim frame in the memory to free up. And this we do by using the page replacement algorithm. Write the victim page out of the disk if it has been marked, if it has been modified. Then read the desired new page into the free frame. Again update the page table and restart the process. So let's talk about the page replacement algorithm. The ultimate goal of page replacement algorithm to minimize the page faults. So algorithm chooses which page to remove the victim when a page fault occurs. Let's say we are having this reference string 701203040 in this one. That is these pages which we need to access. Now, the first algorithm is first in first out, that is the FIFO. That is replace the oldest page in memory, the one that has been there the longest. Use a FIFO queue. Like for example, we are having 3 frames and the reference string is this one, that these are the pages which we want to access. So initially all the 3 frames are empty. Our reference string 7 is called. 7 is not there, so 7 is loaded in the memory. Then 0, so 0 is loaded in the memory, then 1, then 1 is loaded in the memory. Now the 2 is not here, that means a page fault is here. So we need to replace one of the pages. So we will replace as per the first in first out. That means the page which entered the first will be removed first. So the page entered first is 7. So 7 will be chosen for the swapping. So instead of 7 there will be 2. My reference string so my frames becomes 201. Now next is 0 is required. So 0 is already there, so no page fault. Then 3 is not here. So out of 201, which is the page which was the first count, 0. So 0 will be replaced. Then it's 0 again, 0 is not there, so it will be swapped with 1. Then 4, then 2, 3, and so on. So if you can see how many page faults are there, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are a total of 15 page faults. The other no, the FIFO algorithm suffers from the Biladis anomaly. It is a situation where some pages replacement algorithm, in like increasing the frames, can increase the page fault rate. If we increase the number of frames here, it will increase the number of page faults. Now, another one is optimal algorithm. It says that replace the page that will not be used for the longest period of time in future. It is just a theoretical concept basically for the best case scenario, because you cannot predict in a real that which page will be required in future. You cannot predict the future, but it says replace the page that will not be used for the longest period of time in future. So if you see 701, 7 is here, 0 is here, 1 is here, then you need to use the 2. Now for replacing 2, we need to find which page will not be used for the longest period of time. So if you see in the reference string, 7 will be used at the last. So 7 will be used for the replacement with 2. Now 0 is there, now for 3. If we see 3, which page to choose out of these 201. So if we see 201701, so 1 will be used at the end, right? So 2020, look, 0 2, 0 is required here, 2 is required here, 1 will be required at the end. So we will choose 1 for the replacement. Now 3 is in the reference string, 3 is already there, 0 is already there. Now for 4, which page we need to choose for the swapping out of 203. So if you see 2 is here, 3 is here, 0 is used at the end. So 0 will be used for the swapping. So if in this case you see the number of page fault are 1, 2, 3, 4, 5, 6, 7, 8, 9. In the FIFO algorithm there were 15 page fault, but here it is 9. Then another algorithm is least recently used. It says that replace the page that has not been used for the longest time in the future past. Now, it is based on the past behavior irrespective of optimal algorithm, which is based on the future behavior. So, like 701, now 2. 2 is required. So if we see the page which has been used in the past, so 7 is used in the past, like 107. So 7 will be used for swapping. Then 0 is already there, then for 3. So 0 is used, 2 is used, 1 is the longest time in the future. We are going in this direction. In optimal, we go in this direction, but in LRU, we go in this backward direction. So 3 will be replaced with 1. Then 0 is already there. Then for 4 out of 203. So 0 is there, 3 is there, 0 is there, 2. 2 is the least recently used. So 4 will be replaced with 2 and so on. So if you check the number of page faults, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 page faults. We use some other algorithms also, that is counting algorithms, like least frequently used, most frequently used, but these are not commonly used algorithms due to the high overhead and poor performance. Now, if we discuss about the frames, how many frames should each process get? We can have the fixed allocation in which we can have equal allocation or proportional allocation. In equal allocation, divide m frames equally among the n processes, and in proportional allocation, allocate frames based on the size of the process. We use the priority allocation also, in which a process priority is considered. Higher priority processes gets more frames to improve their performance. Then the concept of thrashing comes. Thrashing is a state where the system is spending more time paging than executing a useful work. So the paging means swapping out, swapping in pages and out and so on. So the reason for thrashing is over allocation of memory. If a process does not have enough frame to hold its current working set of pages, the page fault rate will be really high, and then we need to perform a lot of swap in, swap out. The, the result of which will be low CPU utilization, because operating system will see that thing that it needs to increase the degree of multiprogramming because CPU is idle and it will load more process. It will load more process, that means more processes swap in, swap out. Again, operating system will think that the number of processes are low, that's why CPU is idle, and it will make the situation worse. So for this one, we need to set a working set model in which we need to monitor the set of pages a process is actively using. And we need to ensure that a process is allocated enough frame to hold its working set before it is allowed to run. We discussed earlier also about the translation look-aside buffer. Let's see once more. So translation look-aside buffer, or TLB, it is a small associative high-speed hardware cache inside the memory management unit that holds frequently used page table entries. So basically, the CPU will first of all will check the TLB first. If the page number is found, that means it's a TLB hit. The frame number is retrieved immediately. But if it is not found, that means it is a TLB miss. Then the operating system must look up the page table in the memory and then update the TLB. So the memory access time is effective memory access time is increased. So let's say the hit ratio is percentage of time pages is in TLB. Let T is the time for TLB search plus memory access for a hit. M is the time for memory access for a page table lookup and a miss. And effective memory access time is calculated as hit ratio times T plus 1 minus hit ratio. That is the miss ratio times T plus M. So example, if T equals to 20 nanosecond, M equals to 100 nanosecond, then hit ratio is 80%. And effective memory access time becomes 40 nanoseconds. We use certain memory mapped files also, like instead of using certain standard input files like read and write operation, we can map a file directly into the virtual address space of processes. So the initial setup will cause a page fault, which means we will need to bring the whole file into the memory, and subsequent read and writes can handle as simple memory access. So writes are eventually flushed back to the disk. So what happens if we load the files, whole file in the memory, we do not need to read the file again and again from the secondary storage. So it makes the process fast. If there is any write operation, then we need to update the disk back again for updating the write operations. So it simplifies our file access operations, and it allows you also for the efficient shared memory between processes. So in summary, the memory management provides protection, efficiency, and abstraction. We are having the contiguous memory allocation and non-contiguous. In contiguous memory allocation, there are fixed or variable size partitioning. It is simple but suffers from the fragmentation. We can have internal fragmentation, we can have external fragmentation. Paging is a scheme which eliminates external fragmentation but causes the internal fragmentation. It uses a page table for translation. We use one concept of virtual memory using via the demand paging that allows programs to be larger than the size of physical memory. And for virtual memory, we use or for the demand paging, we use the page replacement algorithms like FIFO, OPT, optimal, LRU, and so on. We use thrashing. Thrashing is a concept that occurs when a system is overcommitted and spends all of its time in paging instead of doing some fruitful task. The TLB is a critical hardware cache that makes the paging practical. So that's all for the week 3. Let's meet again for the week 4. Thank you so much.